Okay, I think we can get started. So hello everyone, and thanks for joining me today for this webinar on pipeline in FCS Express 7. I have to say that I'm super happy to be here with you. We waited for this release at the Novo software for a long time. It was really hard job. We invest a lot of effort in this, and we really hope that this will be a great help for your high dimensional data analysis. So let me also start saying a big thanks to our developer teams because they really worked hard in the last months to make all this possible. So enjoy the presentation. Again, if you want to ask any question real time, just navigate to the question section in the GoToMeeting window. And either me or Kaya Ghosh online, we will take care of answering the question in real time. So the agenda of today, it's pretty dense. As usual, I want to start with some background, some definition, some introduction. We will see what's a pipeline. We will see how a pipeline usually looks and why pipelines are so useful and why at the Novo software we decided to make these type of things available in FCS Express 7. Then we will focus on pipelines in FCS Express 7. We will see how to create a pipeline, and we will see all the available steps that you can combine to create a pipeline. Of course, we will doing this either by looking at some, let's say, screenshot and some theory, some slides, but also we will do it practically. So we will create a pipeline together. It will be a 4 or 5 steps pipeline, and we will create it really step by step. As you can see here, I want to add, just to anticipate, some scaling, some downsampling, dimensionality reduction, clustering, some data cleaning, and so on. Okay, so what's a pipeline? Pipeline, as you can see here, is a set of processing elements, and usually they are like mathematical calculation. The key point is that they are connected in series, okay? As you can see here in this little picture. So A goes to B goes to C, and so on. The key point is that the output of each step, let's say the output of calculation A, is usually the input of the next one. So it's the input for calculation B. So pipelines are not new. They are at the basis of programming and computing. So they are very well known. They are used every single day by mathematicians, physicians, programmers, developers, biostatisticians, and so on. Also, I will say all, but let's say most of the algorithm used in flow cytometry for high dimensional data analysis, I mean flow cytometry, mass cytometry, image cytometry, are pipelines themselves. Okay, they are usually provided as a standalone algorithm. Okay, but they are pipeline themselves. And just to mention few, FlowAI or tSNE, FlowSOM, UMAP, whatever. Now, the actual beauty of the pipeline is that a pipeline can be a step of another bigger pipelines. Okay, this is exactly what's missing in most of the flow cytometry data analysis software nowadays. So algorithms are provided as a standalone algorithms, and they cannot easily be combined together. And this is one of the reasons we worked hard to implement pipelines in FCS Express. And as you can see here in this picture, so the small pipeline that we mentioned at the beginning, ABCD, can be just one step, like step 2 of a even bigger pipeline. Now, usually, if you speak with a bioinformatician and you ask how a pipeline looks like, well, it looks like this. It's not definitely user-friendly. So you may ask why people want to use pipeline. Well, because they are really powerful. So the beauty, the good news is that thanks to this feature in FCS Express, you will not have to learn a programming language like R or Python or MATLAB or whatever to create pipelines. So you will not have to deal with anything like you see in this screenshot. Okay. So what are the main advantages of pipelines while programmers are using pipelines? those three are the main advantages. So flexibility, combinability, and reproducibility. So pipeline are super flexible. You can ideally create infinite pipelines by combining multiple steps in different orders. So it's like creating a language with an alphabet, right? So you can combine the letter basically as you want. There are some rules, okay, some guidelines maybe, but at the end, it's super flexible. Then combinability. With this, I want to say that, let's say that in a pipeline you want to use multiple times a specific calculation. Let's say downsampling. Okay, since pipeline can be combined, okay, you don't need to recreate, recode, redevelop every time the same step. You just do it once and then you recall it in the pipeline at any step you want, and you can also recall it in multiple pipelines. So this is a huge advantage for us that can now release new algorithm in a much faster way for you. So if you have any input, any desire, any wish about new algorithm, this advantage of pipeline will really help us in satisfying that needs very quickly. And then reproducibility. This is one of the main advantage of pipeline. And why I say that pipelines are reproducible? Well, let's say that since you have this sort of step-by-step procedure that can be saved, can be stored, okay, you can run this series of calculation at any time you want, multiple times on multiple data set, okay? It's like a recipe, and you can follow that recipe every time you want. So this is something that it's missing in flow data analysis software nowadays. So since algorithms are provided as standalone, okay, piece of calculation, let's say, you need to run one, then you need, for example, to save and export the data to create a new FCS file or a new CSV file. Then you need to re-import if you want to make calculation on the data generated on the first algorithm, okay? Every time you add a new step, a new export, a new import, and then maybe data are saved as CSV, then are saved as PDF, and then you need to take a screenshot. It's really time consuming, and it's hard to make that type of workflow reproducible. And we want to avoid that. We want to make everything really reproducible so that you can do everything inside FCS Express. So if you carefully look at this slide, you can really see that those are the same requirements that should be, let's say, fulfilled when you run high-dimensional data analysis in cytometry. So you need to be flexible because every data set, every experiment may require different algorithms. Combinable because you want to combine different algorithms. You don't want to run a FlowSOM standalone and a UMAP standalone. Maybe you want to run FlowSOM on the UMAP results. Or maybe you want to first do a PCA and then run FlowSOM and then whatever. And of course, everything must be reproducible. So those are the reason why we decided to implement pipeline in FCS Express. And this is the usual workflow in high-dimensional data analysis in flow cytometry. So as you can see here at the top left, you have your data, and then you start analyzing them, let's say with some quality control step. And maybe you want to remove bad events caused by some fluidic issue. You want to remove doublets. You want to remove dead cells. Then you start to perform some other pre-processing step. Pre-processing step are all the steps. It's a kind of general, let's say, category. All those steps that comes before the actual core part of the analysis, like before the clustering, before the dimensionality reduction. Pre-processing step can be like very simple, like gating on the population of interest. So you are selecting the population, selecting the parameters that you want to use as an input, scaling the parameter. This is super important. Normalizing, downsampling. At some point, you have your pre-processed data set, and then that's the point in which you start really running the core part of the analysis. Again, you may want to run some dimensionality reduction, some clustering. You see here a few examples. Maybe you want to run both. Maybe you want to run 3. Okay. I know someone it's running like FlowSOM and UMAP or SPADE and tSNE, whatever, in parallel, and they just use one to backgate the results of the other. That's fine. Some other people want to use a clustering like FlowSOM on the dimensionality reduced data set, not on the original data set. So this is another approach. And without the pipeline, you cannot really do that. And then, of course, at the very end, you want to put together the results and make some presentation, some publication, and so on. So you can really see that this is a very let's say a very good example in which you can apply a pipeline, okay? Because more or less you are always going through the same set of steps. Now, this was our goal. So we wanted to implement pipelines to make complex algorithms very easy to use, thanks to the PowerPoint-like user interface in FCS Express, very fast. I will never mention this enough. We are always implementing all the algorithms directly in FCS Express. We are not relying on any external software. We are not relying on any plugins. So everything is coded into FCS Express. This is why it's super fast. Then combinable, you will see this is basically the key point today. Reproducible, just save your layout in FCS Express and all the pipeline is there. And integrated into a unique platform, which is FCS Express. So you can use like backgating, you can use, I don't know, heatmap, you can use bar chart, whatever you want. So this is just, for example, a graphical summary of what I wanted to show you. So everything is in FCS Express. This is just a screenshot. Here, let me also bring this layout. This is a live layout. It's the same layout I took that screenshot. You see I have my pipeline. No worry about the details. We will see this later on. I have a plot with optimized tSNE. I have a plot with UMAP. I have a plot with FlowSOM. At the bottom left, I have a heatmap you see here. Then I have a bunch of box and whisker plots, okay? This is all inside FCS Express with the beauty that, for example, let me create a gate here on my optimized tSNE. Let's say gate 1, red, click OK. Now you see I can backgate this on my UMAP. I can also apply this gate, for example, on FlowSOM and follow where my events are going. You see, just move the gates and everything move in real time. So this is the beauty. This is what you will be able to do with this new release. This is what we are going to do together today. Okay, so let me close this. Let's go straight. When you want to create a pipeline in FCS Express, so again, a pipeline is a set of calculation. Just go to transformation. You see here from the tools tab and open the transformation dialog. This is the same dialog where in the past, in the previous version, you could add, for example, standalone transformation like k-means, PCA, SPADE, tSNE, and so on. Now you see we have this new entry. It seems like a small enhancement, but you see this will really open a lot of new possibility. So just go to tools, transformation, click on the plus, click on pipeline. Once the main pipeline body, we call this main pipeline body, is added to the transformation, then you can start adding steps. And you see here, we have organized, we have, I would say like 50, 60 different steps. So 50, 60, 60 different mathematical, let's say, calculation that you can perform. And we try to organize them in a nice way so that to make your life easier. You see, we have grouped them in the downsampling steps, dimensionality reduction, clustering step, visualization, mathematical, quality control, some miscellaneous steps, we will see that. And also, as I was mentioning at the beginning, some of the very well diffused algorithms nowadays are pipeline themselves. So instead of letting you add a single step to recreate those algorithms, we created this predefined algorithm category from which you can automatically create a Flow AI pipeline, a FlowSOM pipeline, a SPADE pipeline, and so on. So example of pipeline, again, you can create infinite type of pipeline. But for example, on the left, you have a very simple pipeline. just a scaling step and a UMAP. On the right, you have something more, let's say, advanced. You have a flow AI as a quality control. You have a downsampling. You have a scaling, a normalization, a FlowSOM for clustering, and then you have two-dimensionality reduction with UMAP and tSNE. We will create something in the middle, let's say 4 or 5 steps. Now, the main pipeline body, when you add the pipeline, allows you to define 3 different, let's say, options. The first one is which is the input population for your pipeline, okay? This is, in flow cytometry, this is defined by selecting a gate, okay? A gate from this drop-down menu, and every gate you created in your layout can be selected. Then, which are the input parameters? So the parameter list, the software doesn't really know a priori which parameter list you want to access, right? So when you populate this list, you see you need to select a template file. Likely FCS Express is pretty smart. If you are dealing with a file in your layout, FCS Express will automatically select that file. If you're not happy with that, you want to select something else, just click on these ellipses. Now, every parameters that will be selected here will be available within the pipeline and will be available at the very end as a final results. If you do not select some parameters, let's say that you do not select the time for some reason, the time will neither be available within the pipeline nor as a final results at the end of the pipeline. So once you will apply the pipeline on your plots, the time will not be there because we excluded it here. So as a, let's say, general suggestion, I usually say just select everything here. Every single step in the pipeline will allow you to define which parameter you want to actually use in that step. So this is just a general selection. You will see you can do right-click, select all. The third option here is the suffix. So you will see when you apply the pipeline to a plot, a suffix will be added to the plot title. And by default, the suffix is pipeline transformed. Well, why we allow you to change these? Because you may have multiple pipeline. You can apply multiple, one pipeline to one plot, another pipeline to another plot to compare the results. So if you, let's say, customize the suffix, it would be easier for you to immediately see which pipeline is applied to which plot. So let's create the main pipeline body together. This is a very blank layout. I just created one plot and one gate. You see nothing special. Of course, your analysis can be as complex as you want, okay? 100 plots, 20 different pages, 50 different gates, it doesn't matter. Go to the Tools tab, go to Transformation, open this drop-down menu, go straight to Pipeline. Okay, this is the main pipeline body. You can rename it again with the same idea that you can have multiple pipeline. I will keep new pipeline. And here we go. So as we saw, you can define which is the input population, which is the gate that you want to use. Then which is the template file. You see I was dealing with that file, so FCS Express automatically grabbed the parameter list from that file. I already want to anticipate that you have 2 options actually. You can retrieve the parameter list from a file, or you can retrieve the parameter list from a plot. We will see these later on when this might be useful. Now I'm just retrieving from the file, okay? And this is my parameter list. I can select one by one. I can right click here. You see I can select all, deselect all, inverse selection, whatever. And then this is the suffix, okay? So if I apply, let me draw a plot here, okay? If I apply now this pipeline by drag and drop, for example, this pipeline is doing anything now. So you see now my plot says pipeline transformed, okay? Another way in which you can apply the pipeline is by clicking on here, apply to selected plot. You can also apply to all plots. If you want to, for some reason, remove the pipeline results from these plots or from multiple plots, just go to Format and open the overlay. So you see here the overlay dialog, it's the classical overlay dialog in FCS Express, allows you to define whether a transformation is applied or not. And if you have multiple, which of the many transformation is applied. If I say none, now you see that the plot title doesn't report any suffix. Okay, so now that you know how to create the main pipeline body and what are the options here, let me go back to my presentation and let's see which are the available steps in the pipeline. You already know that there is a little drop-down menu. We will see this later on, and it's subdivided in different categories. One of them is the quality. Then we have mathematical, downsampling, dimensionality reduction, clustering visualization, and miscellaneous. We will go through all those categories. We will select one from each. Now, the first one is the quality control. I want to present this as a first category, even if the example that I want to create with you will be presented at the end. Why is the first that I want to mention? Because usually the quality control is the first step. We have free quality control. You see here, dynamic range, flow rate, signal acquisition. The dynamic range, it's a good way to remove like events that are over the range, either in the highest or in the lower channel. The flow rate check, quality control, the stability of the acquisition, meaning that ideally, if everything goes well, the number of events acquired in every, I would say, seconds should be constant, right? While if you have an interruption, a bubble, or whatever, you see some fluctuation, and those are the bad events that you want to remove. Signal acquisition, it's a quality control that allows you to double check that the intensity, not the rate, it's constant. So if you have a population which is 10 to the 4, it's supposed to be 10 to the 4 from the beginning to the end. If you see fluctuation in the intensity, like it goes up and down, there is something going on with the laser, with the fluidic. Anyway, you may not know, but you want to remove those bad events. Now, while we have these three different quality control checks, because those are at the basis of Flow AI. So Flow AI, it's running those three steps. If you want to run Flow AI, and this is what we will do at the end, instead of adding them one by one, you can just go to the predefined algorithms and click on Flow AI. Again, we will come back later to Flow AI later on, and you will see why, because it's a kind of special algorithm with some particular requirement. Okay, mathematical step. You see here we have this category. We have 5 different mathematical steps. And below, you can see just few examples. So what we will create, I mean, the practical example that we will do will be to add a scaling step, which is basically always required. I mean, what we will see at the end with Flow AI, that's a kind of exception. But most of the algorithm, like tSNE, UMAP, K-means, FlowSOM, SPADE, they all benefit from an initial scaling step. This is exactly the same. This is not something crazy, right? This is something that we always do every day when we plot data in our plots. Okay, we are not looking at fluorescences with a linear scale. We are looking at fluorescences with B exponential, log, hyperlog, arcsine scale for people dealing with mass cytometry. The only scenario in which that I can think about when we look at fluorescences in linear scale, it's like DNA cell cycle. But otherwise, you always use some sort of scaling. And why? Because if you look at the first plot at the left, your FCS file store data as a raw data, as a unscaled data. Okay, so what you will see without applying a scale will be something like this, with a very dense and small negative population and a very broad and spread positive population. Okay, this is not what we are happy to do. Okay, so this is why we always apply a scale. Now, we are doing this in plots and in histogram to make the positive and the negative population more comparable. Okay, technically to stabilize the variance, so to make the variance more comparable between the two populations, or anyway along the range, let's say. Now, algorithms most of the time rely on distances. Okay, so if you run your algorithm on the raw data that you see at the left, the clustering, the dimensionality reduction, it will be not as good as if you would apply the scaling. Okay, so for example, here I have applied to the raw data a scaling step with B exponential scaling. The scaling step is the third one that you see in the mathematical category. And you see here, this is the bi-exponentially scaled data, okay? And also, you see that the label of the axis says CD8 APC size 7 area scaled, okay? Now, just to show you, I have then applied a normalization, okay? This is the normalization step. Normalization step, divide every single value in that parameter by the standard deviation and then subtract the mean. Basically, you are centering your distribution on 0, so the mean will be 0 and the standard deviation will be 1. And you can see in this, in the third example that you see below, okay, those are bi-exponentially scaled and normalized, okay? The shape is the same, but the value are different. You see that the value on the left goes between 0.4 and 8.8. After the normalization, they are centered on 0. And in this case, it goes between -2 and plus 1.3 on the y-axis. The very last was bi-exponentially scaled and 0.1 scaled. What does it mean? The 0.1 is the first one that you see in the list. 0.1 basically, I will say resize. Okay, it adjusts the range of the input data between 0 and 1. Okay, the advantage of this is that if you do this with multiple parameters, they will all be scaled at the same way. And indeed, you see in the last plot on the right, the CD8, both the CD8 and the CD4 now have a minimum of 0 and a maximum of 1. Now, we will not do anything, let's say, super advanced today. I just want to create a scaling step because, again, 99% of the time, it's a beneficial step for the downstream algorithm. So let's go here. Okay, we are here, new pipeline. Okay, we open this drop-down menu, we scroll down to the mathematical, and we add a scaling step. Okay, you can rename this, and you can flag all the parameters that you want to scale. Now, you see here at the bottom, you have the automatic checkbox. Automatic means that the instrument-specific setting will be applied. So in FCS Express, we have instrument-specific setting. By default, unless you change them or whatever, in this case, I'm dealing with a pretty standard FCS 3.0 file. By default, the instrument-specific setting for this type of data are to scale fluorescences with B exponential and scatter parameter and time with linear scale. So if I select all, it means that they will be all scale, but time for a scatter size scatter with linear scale, fluorescences with B exponential. Now, let's say that I only want to scale these fluorescences with B exponential. And maybe I want to scale the for scatter size scatter with log. Okay, you can add as many steps as you want of the same type. Now you see I have a new scaling step. Okay, I can rename it. I can say scaling for scatter, let's say. And, oops, sorry. You can add as many steps as you want. And this also allows me to show you that, remember the initial definition that we said about the pipeline. The output of one step are usually the input data for the next step. So in the next step, I have access as input data, both the original data, but also the scaled data that comes out from the first one. Now, I don't want to select those data because I don't want to scale them twice. In this case, what I will do is simply click on for a scatter size scatter and select the scale that I want. Okay, so in step number 3, whichever will be the step number 3, I will have access to the scale data for a scatter size scatter log and for fluorescences B exponential. Now, if you don't want to do to run a step, you can remove it. Okay, you can also, sorry, you can uncheck it. It will not be run. You can also completely remove it. Just select and press on the red cross. So let's keep things simple. We will just select 6 different fluorescences. We will scale them automatically. And in this case, it means by exponential. Now, what other step we can add? Downsampling step. We have 5 different type of downsampling. The easiest one, the one that you can always run, I would say in every flow software, are random sampling and interval sampling. Random sampling is just keep fewer events selected randomly. Interval sampling, it's basically the same stuff, but it's faster. So let's say you have 100 events, you want to sample 10 events with interval sampling. FCS Express will sample events 1, 11, 21, 31, 41. It's still random at the end because your data have been acquired, your events have been acquired randomly from the tube. Okay, so it's still random, but it's faster and it's more reproducible. Then we have two types of downsampling that belong to the family of density-based downsampling, which are the target and the weighted density downsampling. I have few slides from these because I think they are really cool. I'm going to insert the interval sampling now, which is the basics, let's say, and then we will come back later to the density-dependent downsampling. So this is my pipeline, okay? Super happy to add a new step here, downsampling, interval sampling, okay? Now I can say I want to downsample to 1,000, to 5,000, to 10,000, whatever you want. I want to mention, we will not go into much detail. We will probably organize dedicated webinar on downsampling because it's a very interesting topic. You see here we have two options. The default one is downsample existing parameter. What does that mean? After this downsampling step, we will have 10,000 events. Of course, if you have more than 10,000 at the beginning. But let's say if you have 10,000 and you downsample to 1,000, after this step, you will only have the 1,000 sampled events. The unsampled events will be completely, let's say, removed, okay, from this step. It means that the step that will come after this one will only deal with 1,000 events, okay? So this is what you usually want to do. However, you can also use the second option, create a mask parameter. This means that this step will not really downsample straight away. It will just label each event with a 0, like bad, or a 1, good. Okay, if you say I have 10,000 events and I want to downsample 1,000 and I want to create a mask parameter, 1,000 events will be labeled with 1, and like 9,000 events out of 10,000 will be labeled with 0. Why you may want to do that? Because you may want to run the next step, okay, on all events and still being able to then simply keep the previously downsampled file. This happen if the calculation that you want to run after this downsampling step somehow can be different if run on 1,000, 2,000, 10,000 cells. So again, this is very cool. We cannot go unfortunately into much detail, so we'll keep the default one. This means that after this step, we will only have, let's say, 10,000 events. This also allows me to mention this fifth type of downsampling, max downsampling. Okay, let's say that you have multiple downsampling, one after the other, and each of them create a mask. So each of them label events as 0 or 1. 0 are the bad guy, 1 are the good guy, the one that you want to keep. With a mask downsampling, okay, you can add a max downsampling downstream and say, I want to remove all the events that have all 0, okay, from the 3 previous steps. It means all the events that have been flagged as a bad guy by all the previous steps. Or you can say, I want to remove only the event that have been flagged at least once as a bad guy. So it's a really, really cool stuff. About the density-dependent downsampling, I have 2 slides because I think it's really worth mentioning. So what's the limitation of the standard interval sampling or random sampling? The limitation is that you may lose rare events. Okay, this is also the reason why downsampling it's usually considered a bad stuff. Okay, because yeah, you speed up the calculation, but you may lose rare events. The only thing that you can do is to increase the sample size and wait longer, for example, for the calculation, or go to a better computer. But that's not really always true. So there are other type of downsampling. The issue is that simply Flow software doesn't allow you to do that. You can do that with R or Python, you can also do that with FCS Express. So on the left, you have a data set. You see here with 7 different population with decreasing frequency. So the first one at the bottom left, it's gate 7. You see here, it's 100,000 events, 61%. And the last one, the red one, is the rare population, just contain 20 events. So it counts for 0.01. Also, the blue one, it's not really frequent. You see it's 0.06. So we are dealing with really rare population. Now, if you perform interval sampling or random sampling, doesn't matter. You see here, if you sample 5,000 events, which are few, let's say, you only sample, if you're lucky actually, 1 cell from the red one and 2 cells from the blue one. Okay, this means that you will probably not be able to cluster those cells as actual clusters, as actual population, because I mean you didn't sample enough. It means that the algorithm will not probably be able to understand that those are 2 population, or even that those 3. So the last rarest 3 are 3 different population. They will be probably, let's say, considered as a unique population. Again, the only thing that you can do is to increase the sample size. Or in FCS Express, you can switch the type of sampling. And here you see I have just run this with the weighted density. It's one of the 2 downsampling available. The idea is that you preferentially sample rare population. And indeed, you see that, have a look at the red and at the blue. Okay, instead of 1 and 2 respectively, from the interval downsampling, now we are sampling 14 and 17. So you are really increasing the chances to find and to cluster and to isolate those population. Okay, if you're running tSNE, you increase the chance to have an island for those two islands, sorry, blue and red. If you're running FlowSOM or k-means or SPADE, you are increasing the chance to consider them as 2 separated population. Now, someone may say, yeah, but the frequency are now, let's say, skewed. That's fine. Okay, this is expected, but this is actually what I want here. The point here is to being able to find that population. Okay, once you have find it, you have clustered it, you have an island in tSNE or UMAP or whatever, you can phenotype it, and then you can always go back to your original data set and calculate the frequency, but at least you can find it. And this is just a test that I've done with tSNE on this data set. Okay, it's 160,000. It's not huge. It was just an example. It may be like 1,600,000. It doesn't matter. And of course, the goal is to being able to separate the most rare population. Okay, in this slide, the rarest is the green, and let's say the second rarest, it's pink. Okay, so the goal is to discriminate those. In a tSNE plot, this means that you should have 2 islands, small, but 2 separated islands for the green and for the pink. Now, if you look at these, on the left, you have the tSNE on the interval downsampled data. So I increased the sampling up to 48,000 out of 160,000. It means 30% of the events, and tSNE, it's not able to discriminate the pink and the green. I can tell you that the pink is and the green are all stuck together at the bottom left. So these, let's say, small rectangle green, it's containing both of those populations. So the only thing that you can do is to increase the sampling. Instead of 48,000, go up, go higher. Now on the right, okay, you have the weighted density downsampled. Okay, the tSNE might not look so sexy, let's say, because you have fewer events. In this case, you only have 8,000. But again, the main goal was to being able to find the rare population. And with this weighted density downsampling, with just 8,000 events, you can clearly see at the top right of my tSNE plots, 2 little islands. One is really, really, really small. It's the green one, and the other one is the pink one. Okay, the advantage here is that you can run tSNE like 10 times faster. In this case was 13 times faster, but the overall advantage is that you can find the population, while with just interval sampling, which again, this is the default like downsampling that you can find in any other software, you cannot. Now, let me zoom out and let's go to the core part of the of our pipeline, dimensionality reduction step. We have so far UMAP, which is new. We didn't have it in the past release. Then tSNE, tSNE, and then we have principal component. And you can find them in the dimensionality reduction category and listed here. So we will add UMAP just because it's new. And let's go here. So click on pipeline and click on the little plus drop down menu, go to dimensionality reduction, UMAP. And now you see that in the UMAP, we have access as an input, as possible input data, the original data, the unscaled, and the scaled data. So let's select all the scale data, for example. We will not go into much detail with UMAP, but you see you can change a bunch of different options like the number of neighbors, the minimum distance in the low dimensional data set, and so on. But you see, UMAP, it's now just one step and it's very easy to add it. Now we will also add a new step, which is a clustering. Okay, and in this case, we have really a lot of type of clustering. So from the predefined algorithm, together with Flow AI, which is a quality control, okay, you have two, let's say, mini pipeline, which are FlowSOM and SPADE. We already had SPADE in the past. Now we have FlowSOM. And I also want to mention that tomorrow we will have a webinar dedicated on FlowSOM. Then we have single step that perform clustering, and you can find them in the clustering category. We have consensus clustering, which is also used by FlowSOM, hierarchical clustering, which is also used by FlowSOM, k-means, which is used by SPADE, for example, self-organizing map, that's the core part of the FlowSOM algorithm. And then you have visualization step. So in the visualization category, you have two steps, the minimum spanning tree and the graph layout. Those basically go together because those are the one used by FlowSOM and SPADE also to actually visualize the cluster. Otherwise, it's not like this in SPADE that you are visualizing events. You can just use the dot plots. In this case, you are visualizing clustering. Usually, I mean, most of the time, they are visualized as nodes, as a circle, okay? And those two steps, the graph layout and the minimum spanning tree, are the one required to create that tree, okay? The SPADE tree, the FlowSOM tree. And so let's go back here. And after the scaling, the downsampling, and the UMAP, okay, we can click on plus. And now I don't want to create FlowSOM step by step. I go straight to the predefined algorithm and I click on FlowSOM. Now you see that multiple steps are added, okay? The first one is a scaling. Actually, we do not really need it now because this is okay if FlowSOM, if we want to use it as a standalone, but we are scaling already at the beginning of our pipeline. So I can either uncheck this or I can completely remove it. Then we have the self-organizing map step. This is the core part of the FlowSOM algorithm. Let's run it on the same parameter that we use as the input for UMAP. So we will really compare apple with apple. And this is the crazy part. This is super, super, super cool. You can, if you want, run a clustering, in this case, FlowSOM, on the dimensionality reduced data set. So on UMAP 1 and 2, or on tSNE X and Y, whatever. This is something really amazing. Then we have the minimum spanning tree and the graph layout method. Okay, those run on the output of FlowSOM. Those are intended to really plot the FlowSOM tree. Then you have the consensus clustering. Okay, this is also using as an input parameter the sum cluster. The consensus clustering is a step that allows you to cluster clusters. Okay, while the new self-organizing map that you see at the top of the FlowSOM, it's clustering event, the consensus clustering, it's clustering clusters. Okay, it's really great. This is depicted in the FlowSOM tree as an halo around the nodes. We will see this in a few minutes. And then you have this step, this parameter removal actually comes from the miscellaneous. You see here, parameter removal. Why you want to remove parameters, okay? It's not really specific for FlowSOM, okay? You can use it wherever you want, okay? I can also drag it out of FlowSOM you see here, and usually you need to keep it at the very end of the pipeline. Okay, why you want to remove parameters? You see here in FlowSOM we are creating new parameter, for example the clustering. In UMAP we are creating two parameters that are UMAP 1 and 2. Those are really what we want. But what about the scaling? Do we really want the output of the scaling step? Do we really need the scaled parameter as a final output? Really, no. I mean, in this case, we just need them as an intermediate in the intermediate step. So at the end, if we want to make the parameter list shorter, we can remove the scaled parameter, okay? Or any parameter that you do not want to see in the parameter list, which will be this one, once the pipeline will be applied. Okay, so now we have just one more category. We already see that is the miscellaneous. You can add folder to make your pipeline more easy to read. You can merge to spectra. This is a way in which you can create spectral data from non-spectral, you can create spectral plot from non-spectral data, so from data from non-spectral instrument. And then you have the unmixing if you want to run unmixing within the pipeline. You have virtual bandpass if you want to create virtual bandpass filter using data from spectral instrument this time, so to mimic some non-spectral instrument. And you can find a nice webinar on the merge to spectra on our website. Okay, so before moving there, we are here. Okay, we have a plot gated on the population of interest. We have our pipeline. We have all our steps. We already know that we can drag and drop the pipeline on top of the plots. And now the pipeline it's run. And now you see pipeline transformed in the title. This means that I have access to the output data. You see I have UMAP 1. Let me zoom in. Okay, let me resize this. We have UMAP 1 and 2. Those comes from the UMAP step. Okay, we also have the SOM cluster assignment. These come from the SOM step. Okay, it doesn't really, let's say, it's not really user friendly when you look at it on a 2D plots. So let's go back to UMAP. A much better way to look at the SOM clustering is by inserting a plate heatmap. Okay, plate heatmap are useful in FCS Express to display, plate-based experiment, but also clustering. And you can see here you have now your FlowSOM tree. And again, we will spend more time tomorrow on FlowSOM. I just want to show you how to create it. And also for UMAP, we will be glad to schedule other webinars to focus on this. Now, let me go back to our presentation and let me speak about Flow AI. So the quality control that I was mentioning at the beginning, and you will see why I decided to keep it at the very end. So Flow AI performed 3 quality control. So the flow rate, meaning that it checks whether you have any outlier. Let's say that in a second you acquired, I don't know, 100 events. 100 events in the second later on, other 100 events, and then for some reason at a given time during the acquisition we have 1000 instead of 100, and maybe the second later on it's 0, the acquisition is 0. So if you see any of those, let's say, fluctuation, probably something went wrong during the acquisition. So Flow AI, thanks to the flow rate, will remove those bad events. The signal acquisition does the same stuff, but instead of looking at the flow rate, it's looking at the intensity. So ideally, if you have a population that emit like it's bright 10 to the 4, should be 10 to the 4 for the whole acquisition. If it increase or if it decreased the intensity, something it's wrong. So Flow AI will detect those events and will remove that. Last but not least, dynamic range. Every instrument has, let's say, a last channel, let's say 200,000. Every event which is brighter than 200,000, it's simply recorded as 200,000. Okay, you don't know whether it's 200,001 or 200 or 2 million. So Flow AI can remove those outlier and can do also the same in the lower range. Now, FlowAI, it's quite special than the other algorithm that we mentioned, like UMAP, FlowSOM, and clustering and dimensionality reduction, because it must be run on linearly scaled data, okay? So on raw data, not on B exponential scale, not on log, on linearly scaled raw data. And it must be run on uncompensated data. So how can you access to linearly scaled raw data and also uncompensated data in FCS Express? So for linearly scaled data, the solution is pretty intuitive. So simply add the FlowAI step upstream any other scaling step. Okay, so we started in our pipeline with a scaling step. If you want to add FlowAI, first add FlowAI and then scale the parameter. So that's okay. What about the uncompensated data? So historically in FCS Express, when you load the data that comes with a compensation matrix, the compensation metric is applied and you do not even see the uncompensated data because usually you don't really need the uncompensated data. But FlowAI requires the uncompensated data. So we added a layout options so that allows you to access uncompensated data. So let me just open a new layout. This is a brand new layout. And what I'm going to do is to go to File, and then click on Info, Layout Options. If you scroll down, you will see an option that will, it was not there. So the option is this one. Let me underline it. It's New Compensated Parameter. What do you want to do with them? You want to override the uncompensated parameter. So you want to basically only see the compensated in the parameter list. This is the default behavior of FCS Express since version 1. Okay. Now you can choose. You have this second checkbox. You can append to data. So, and actually you will append after the uncompensated data. So in the parameter list, you will have all the uncompensated data, and then you will have the compensated data. How you will discriminate between them? Well, the compensated data will be named with a suffix. In this case, you can change it, but by default, it's -comp. So let me clean this up. Let me click on append and let me click OK. So now in this layout, why we set it as a layout specific option? Because it doesn't, I mean, it may happen that you don't want to access uncompensated data every time in every layout. So you can change it on a layout specific base. Now, let me go to data. Let's load the same exa file that I was using before. Okay, let me drag and drop it. And now you can clearly see that in my parameter list, I do have access to both the uncompensated data, so the first one, the first set, and the compensated data. Now, if you want to run the pipeline, okay, just go to Tools, Transformation, Pipeline. Okay, select the gate if you want. Now you will see the usefulness of this drop-down menu. Remember, you can select from the file, and in the file you have this parameter list, or you can select from the selected plot. Now, if I select the template, so the parameter list from the selected plot, I will be able to access both the uncompensated and the compensated data. So here, what you will do would just to select all and go and add, for example, FlowAI. Here we go. We have a flow rate check. We have a signal acquisition. Okay. In this case, I will only run, for example, the signal acquisition on the non-compensated data because this is what FlowAI require. You can or cannot include the scatter. It's up to you. Okay. And then the dynamic range. Okay. Let's do the same. And I will uncheck my compensated data. Okay, now I can apply FlowAI straight away. You see that some events were removed, or I can move on and I can add downsampling, I can add scaling, I can add dimensionality reduction, and so on. Also, I want to mention this little checkbox. So you see here, run option automatically run the pipeline. So the pipeline, if this is checked, it's automatically recalculated every time you change something in some step. Okay, it might not be what you want if you want to perform a lot of changes. Like if you want to add a tSNE, a FlowSOM, a UMAP, probably you want to calculate everything right at the end and not step by step, okay? To not lose time, let's say. So if you want, you can uncheck the automatically run pipeline, do the change you want. For example, I can go to the dynamic range and I can change some, I don't know, I want to include for a scatter, say scatter. You see that when you change something in the pipeline, the plot became blank because we don't want to display something that it's not up to date, right? When you want to run it, okay, just click again on automatically run the pipeline or simply click on execute the pipeline, okay? So this is all what I want to show. Let me just summarize. With FCS Express, now you have this amazing tool, which is the pipeline. So with the pipeline, when you want to run high-dimensional data analysis, it's really, I mean, easy to use because it's in FCS Express PowerPoint-like user interface. You have drag and drop. You can uncheck or uncheck. You have drop-down menu. It's really a very user-friendly interface. Then it's really fast again because we are coding every algorithm directly in FCS Express. We are not using any external software nor plugin. It's combinable, it's reproducible, it's integrated. Remember the first layout that I opened, we had an heat map, we had box and whisker, we have the FlowSOM together with the UMAP, and so on. So last thing that I want to mention is the last thing that you see in this slide. If you have any wish, if you see that you will benefit from some additional steps, either a downsampling, a dimensionality reduction, a clustering, a logical step, whatever, just let us know. We will be super happy to include them in one of the next release. So if you have never tried FCS Express and you want to give it a try, especially for the pipeline, just go to on our website and click on free demo. You can download the full version of FCS Express for 30 days and then just send us an email if you have any question or if you want to sit down and have a little bit of training. So many thanks to all of you for attending. It was really a pleasure. I hope that this presentation was useful and was exciting. And if you have any question, just send an email to support. I'm based in Europe. You see my email. If you are based in Europe, you can also write directly to myself.